All right, so jumping right into example 1-18, I started off by importing all of these functions that are necessary for our calculations and then our plots at the end. And then I started with initial conditions as stated in the example, starting off with these initial values that were given. The problem also gives us these Stefan-Maxwell diffusion coefficients. And then the problem states the bulk phase composition of our components at the beginning. So that's why I have Y1 naught. So Y1 naught, which is ethanol, is 0.6. Y2 naught, which is acetaldehyde, which is 0.2. And Y3 naught, which is hydrogen, which can either be found by subtracting Y1 naught and Y2 naught from 1, or it was stated in the book as 0.2. And the book also gives us our gas film thickness, which is delta. I also went ahead and solved for concentration using a formula that contained some known values. Pressure, the gas constant, and temperature were all given in the problem. And then my initial guess for N1, which I just said was 1. Okay, so our first equation is to initialize our Stefan-Maxwell from equation 1-35 in the book, which is called dy, and it includes our eta, our mole fraction, and our molar diffusion, which is N1. Then I initialize some variables for mole fraction of our components that we wrote above, this Y1, Y2, and Y3. Then looking at the stoichiometric ratio in the initial equation in the problem and using our bootstrap relationship, we can say that negative N1 is equal to N2, which is equal to N3, which helps simplify our equations from here on out, because then everything is just in terms of N1 instead of having N1, N2, and N3. Then, using equation 1-35 from the book for a multi-component mixture of ideal gases, I apply it to our tertiary mixture to get the following formulas. These two, noting that all of the molar diffusions are in terms of component 1, so they're all N1, so anywhere that would have been an N2 or an N3 is now a negative N1. The next section of code goes through our initial value problem to find y solve, which is a differential equation, and uses our dy1 and dy2 equations as we stated above, and is called upon as just dy. This will give us our mole fractions with respect to our molar flux from 0 to 1, with initial values of y1 naught and y2 naught. The method and dense output just means that it will be solved continuously between our 2 points that we gave, that one, 0 and 1. This will return a manipulation of the first order reaction boundary condition, which just states that N1 is equal to K times Y delta. We just rearranged it so all the values are on one side, so the whole expression is equal to 0. The molar flux can be found here using the root function, using our N1 guess from earlier, which I had as 1, right there. Then this line is just so my answer is a little bit clearer and easier to understand. Then this line solves for the composition at the interface at delta, where it's the same argument as above, but this time instead of inputting N1, we are inputting the correct argument for N1, which is this answer.x. And then here are our mole fractions and our correct N1. Now these lines are just for creating the graph. We start by defining eta, which is Z over our film thickness, evenly spaced out 11 times. And then this line specifies the actual Z position throughout the graph. Then these two lines specify the Y1 and Y2 mole fractions at each Z position. And then this section actually makes the plots. Here, y1, y2, and y3. Here's y1, y2, and then y3 is kind of calculated, but it's just saying it's 1 minus y1 minus y2, like we stated at the beginning. The y-axis is the mole fractions, and the x-axis is the z positions. Then you can, looking at the graph, you can use your cursor, you can follow the change in mole fraction of the various components. You can see the 60% or 0.6 mole fraction of ethanol at the very beginning, and then the 0.2 mole fraction of both acetaldehyde and hydrogen also at the start. And then we end with ethanol dropping to 0.08, acetaldehyde increasing to 0.58, and hydrogen also increasing to 0.32, which adds up to 1, just like I did at the beginning. So our mole fractions all work and all of our numbers make sense.